Hello everyone, I'm Elifnaz Sağlamkaya. Here I'm going to give a brief summary of our paper on self-doped electron transport layers and their effect on active layer properties such as bimolecular recombination and static disorder. Here we are looking at the current voltage curves and device parameters of a very well-known system PM6Y6 paired with two different ETLs. Before we start, to give a short definition of self-doping, a self-doped molecule is a molecule that has its counter ions already covalently attached to its core. Both PDNN and PDNO are self-doped. Here the electrons of N-oxide group of PDNO and electrons of the secondary amine groups of PDNN are able to delocalize to the electron deficient perilindimide core. PDNO is a very common ETL for PM6Y6 and has shown to have good compatibility with the system, both in terms of energy levels and for the fact that it does not cause any surface recombination. Nevertheless, switching to PDNN increases the efficiency noticeably. This increase in the efficiency is due to the higher fill factors and higher VOC values for both 100 nanometer and 200 nanometer active layer thickness. First, we investigated the doping strengths of these ETLs by combining two different methods. First, the electron paramagnetic resonance spectroscopy is a method that's sensitive to unpaired electrons, and the PDNN has a significantly higher density of unpaired electron compared to PDNO. But we were wondering how many of these unpaired electrons are actually mobile in ETLs. For that, the Hall effect measurements show the charges that are drifting as a response to the applied magnetic field. And the calculated charge carrier densities from this method show also higher electron density for PDNN, but also the higher percentage of unpaired electrons are mobile in PDNN. So since there are so many mobile electrons in these layers, a question arose about does this affect the doping density of active layer? For that, we made capacitance voltage measurements and did Mott-Schottky analysis on 400 nanometer active layer thickness devices. Indeed, PDNN showed a higher doping density. This is doping density of the active layer, and PDNO has a little bit lower doping density, and when there is no ETL, this value reaches the low level of doping density. So this device shows almost undoped behavior. So presumably there is some charge spilling happening from ETL to the active layer. To see what this changes in the active layer, space charge limited current measurements were employed to measure the electron mobility and static disorder. The PM6x6 electron-only devices have a little bit higher electron mobility when PDNN is used as the ETL, and also the LUMO disorder for PM6x6 is suppressed. So this charge spilling that's taken place is seeming to filling up some states in the Gaussian density of states. Therefore, we are seeing a smaller disorder. Now moving on to the recombination properties, we measured the bimolecular recombination coefficient and measured a smaller coefficient for the PM6/6 with PDA-NAND. Bimolecular recombination have contributions from both radiative and non-radiative channels. By looking at the external photovoltaic quantum efficiency, calculated the same radiative limits for both PM6/6 solar cells, so that the radiative limit does not change, but looking at the electroluminescence spectra, we can see that the PM6/6 with PDNN is a little bit more emissive. And calculating the non-radiative VOC loss from the external electroluminescence quantum efficiency, we again saw a suppressed losses for PM6/6 with PDNN. The non-radiative losses have a direct correlation with the static disorder. There are multiple strategies to suppress the static disorder in order to reduce the non-radiative losses, which are the main loss mechanism in organic solar cells. Here we are presenting an alternative strategy. By using a different electron transport layer, we were able to suppress this recombination channel. Thank you for listening. Stay tuned for more scientific videos from our channel.